The longest any machine has survived on the surface of Venus is 2 hours and 7 minutes. That machine, Venera 13, was a Soviet probe sheathed in titanium, pre-cooled before atmospheric entry, and specifically engineered for the most hostile surface in the solar system. It lasted just over 2 hours before the planet destroyed it. What makes this extraordinary is that Venus is Earth's twin, same size, nearly the same mass, formed from the same cloud of material, orbiting one step closer to the Sun. How did a world so like ours become the most dangerous place in the solar system? And could the same physics eventually do the same thing to Earth? The answer required the most ambitious planetary exploration program ever attempted, and it begins with a mistake that lasted centuries. For most of human history, Venus was a mystery wrapped in light. The brightest object in the night sky after the moon, so brilliant that ancient civilizations mistook it for two separate bodies, the morning star and the evening star. When telescopes became powerful enough to study it closely, the mystery only deepened. A world completely shrouded in thick, unbroken cloud. No one could see the surface. So they imagined. Venus was nearly Earth's size, a little closer to the Sun, but those dense clouds could reflect much of the extra sunlight. In the early 20th century, many planetary scientists pictured a warm, wet world, tropical, possibly covered in swamps and primitive vegetation. The Swedish chemist Svante Arrhenius suggested the clouds might be water vapor. Science fiction populated Venus with jungles, oceans, even alien civilizations. If any world beyond Earth harbored life, Venus, warm, cloudy, Earth-sized, seemed the strongest candidate. Then, in the early 1960s, radio astronomers made the first direct measurement of Venus's surface temperature. Radio waves, unlike visible light, pass through cloud cover, and the signal they detected was staggering. The surface wasn't warm, it was over 400 degrees Celsius, hotter than Mercury, which sits far closer to the Sun. Something had gone catastrophically wrong. Radio telescopes could measure the temperature, but they couldn't explain it. They couldn't show you what lay beneath those clouds, or reveal why a planet so similar to Earth had become something so violently different. To find out, you had to go there. And that is exactly what the Soviet Union decided to do. The Venera program began in 1961. The first probe failed. So did the second, and the third. Through the 1960s, nearly every spacecraft the Soviets sent toward Venus was either lost in transit, destroyed during atmospheric entry, or crushed before reaching the surface. What made this uniquely difficult was that each failure happened in a way the engineers hadn't predicted. They were designing blind, building machines to survive an environment they didn't yet understand, and learning its properties only when those machines died. The engineers of the Lavochkin Design Bureau were solving a problem no one had faced before. How do you keep electronics working in conditions that melt solder? Their approach was elegant in its desperation. Each lander was pre-cooled before entry, its internal components wrapped in thermal insulation that would slow the penetration of heat from outside. They weren't trying to survive Venus permanently. They were trying to survive long enough to transmit something back. It took nearly a decade of failures, each representing years of engineering and national investment, before a single byte of surface data reached Earth. Venera 4 in 1967 was the first to succeed in returning data from inside Venus's atmosphere. As it descended on its parachute, it measured temperatures climbing far faster than any model predicted, and confirmed the atmosphere was over 96% carbon dioxide. Then, at roughly 25 kilometers above the surface, the signal died. The probe had been rated for 25 atmospheres of pressure. Venus crushed it before it was halfway down. So they built the next one stronger. Venera 5 and 6 dove deeper before being destroyed. Each returned a sharper picture of the pressure gradient, and each picture was worse than the last. Venera 7, launched in 1970, was redesigned from scratch, a reinforced pressure vessel rated for 180 atmospheres. On December 15, it reached the surface and transmitted for 23 minutes. The Soviet Union had landed the first human-made object on the surface of another planet. The data was brutal. Surface temperature, roughly 460 degrees Celsius. Atmospheric pressure, about 90 atmospheres, the weight of 900 meters of seawater pressing down on every surface, and all of it at temperatures hot enough to melt lead, tin, and zinc. The Soviets kept building. Venera 9 returned the first photograph ever taken on the surface of another planet, a barren landscape of angular rocks under a dim orange sky. No water, no erosion, no trace of the tropical world anyone had imagined, just volcanic basalt baking under an ocean of carbon dioxide. And then came Venera 13. Engineered to survive 32 minutes, it lasted 127, over 2 hours of continuous data, including color photographs, atmospheric composition readings, and even a drill sample of the rock analyzed by an onboard spectrometer. Those images are still the highest quality photographs ever taken on Venus. They show a world of muted amber light, flat volcanic rocks stretching to a horizon blurred by heat and atmospheric density, and a sky so thick that sunlight filtering through it resembles the glow inside a kiln. This was supposed to be Earth's twin, 2 planets born from the same cloud, built from the same materials, nearly identical in size. Why did one become home to life, while the other became the most hostile surface in the solar system? The answer is the most important feedback loop in planetary science, and it starts with a single molecular property of carbon dioxide. CO2 is transparent to visible light, but opaque to infrared radiation. Sunlight passes through it freely, reaches a planet's surface, and warms the ground. But the warm ground radiates energy back upward as infrared, and the CO2 absorbs that outgoing infrared and re-emits it in every direction, including back toward the surface. The result: the ground receives energy from the sun and energy recycled by its own atmosphere. This is the greenhouse effect. In the right amount, it's essential. Without it, Earth's average temperature would sit around -18 Celsius, and nothing we'd recognize as life could exist. On Venus, the greenhouse effect didn't settle into balance. It spiraled out of control. Venus receives roughly 90% more solar energy per square meter than Earth, not because it's dramatically closer, but because sunlight intensity falls with the square of the distance, and Venus orbits at about 70% of Earth's distance from the Sun. Early in its history, this extra energy warmed the surface. Warmer oceans meant more water evaporated, and here is the detail that changes everything. Water vapor is itself a potent greenhouse gas, molecule for molecule, more effective at trapping heat than CO2. More evaporation trapped more heat, which drove more evaporation, which trapped more heat still. This is a positive feedback loop, and on Venus, it never found equilibrium. The oceans evaporated entirely. Every drop lifted into the atmosphere, amplifying the greenhouse effect ever further. Then ultraviolet light from the sun began splitting the water molecules apart, separating hydrogen from oxygen. The lightweight hydrogen escaped into space, and once the hydrogen was gone, the water could never reform. Venus didn't just lose its oceans to evaporation, they were dismantled at the molecular level and scattered into the void. The proof came from NASA's Pioneer Venus orbiter in 1978. It measured the ratio of deuterium, a heavier form of hydrogen, to ordinary hydrogen in Venus's upper atmosphere. If a planet has been losing lightweight hydrogen to space over billions of years, the remaining gas should be enriched in deuterium, which is heavier and far harder for solar wind to strip away. Venus's ratio was roughly 100 times Earth's. That number is the chemical fingerprint of evaporated oceans, a fossil record of water, written in the air of a world that has none. But the most unsettling part of Venus's story isn't how it died, it's what it was before the destruction began. Computer simulations from NASA's Goddard Institute for Space Studies suggest that Venus may have sustained liquid water on its surface for 2 to 3 billion years. Not a brief splash of habitability before the Runaway took hold. Billions of years of oceans, coastlines, weather, and stable surface temperatures. Venus may have been habitable for longer than Mars ever was. Consider what that timescale means. Complex multicellular life has existed on Earth for roughly 600 million years. Venus may have had habitable conditions for more than 3 times as long. Whether anything lived there, we don't know, but the window was more than wide enough. And all of it, every ocean, every coastline, every trace, was erased by a process so gradual that no observer would have noticed it within a single lifetime. Picture what that world might have been. An ocean planet, orbiting closer to the sun than we do, blanketed by a thick atmosphere that trapped warmth, clouds and rain, waves breaking on volcanic shorelines. This isn't fantasy. It's what the models produce when you give Venus its early conditions and run the physics forward. What tipped the balance? The honest answer is that planetary scientists are still debating. The sun has been gradually brightening, roughly 30% more luminous today than when the solar system formed, and Venus, orbiting closer, felt this increase sooner. Some researchers point to catastrophic volcanism. The entire surface of Venus appears to have been repaved by lava roughly 300 to 500 million years ago, potentially flooding the atmosphere with CO2. Others stress Venus's lack of a global magnetic field, which left its upper atmosphere exposed to solar wind stripping. Most likely, it was all three: a slow stellar brightening, a volcanic crisis, and a naked atmosphere conspiring over hundreds of millions of years. But the critical insight isn't which trigger pulled first. It's that Venus died by drifting across a threshold, a temperature beyond which the positive feedback becomes self-sustaining and the oceans cannot survive. That threshold is defined by physics, not by geography. It applies to any rocky world with water, an atmosphere, and a star that's getting warmer. Which brings us to the question this entire story has been building toward. How close is Earth to the same line? Closer than most people realize. The habitable zone, the range of distances from a star where liquid water can persist on a planet's surface, has boundaries. Earth orbits near the inner edge, We sit closer to Venus's threshold than to the cold outer boundary where oceans freeze. Most estimates place that inner boundary somewhere between 5 and 15% closer to the Sun than Earth currently orbits, a thin margin on the scale of a solar system. What has kept Earth stable is a geological thermostat, a slow feedback loop called the carbonate-silicate cycle. Carbon dioxide dissolves in rainwater, forming a weak acid that weathers rocks on Earth's surface, freeing calcium and other minerals that wash into the oceans. There, the dissolved minerals combine with CO2 to form limestone, which sinks to the seafloor and is drawn into the mantle by the motion of tectonic plates. Millions of years later, volcanoes return the carbon to the atmosphere, completing the cycle. The elegance is in the self-correction. If temperatures rise, more water evaporates, more rain falls, more CO2 is pulled from the air, and the planet cools. If temperatures drop, rain decreases, CO2 builds up, and the greenhouse strengthens. This thermostat has kept Earth within a habitable range for over 4 billion years, even as the sun has grown brighter. But the thermostat has a fatal dependency: liquid water. The weathering cycle works only as long as there are oceans to feed rain and rocks for that rain to dissolve. Venus had this cycle too, once. When it lost its water, it lost the thermostat. And with the thermostat gone, nothing remained to oppose the feedback. The sun continues to brighten. In roughly 1 billion years, perhaps less, Earth will warm to the point where water vapor accumulates in the upper atmosphere faster than weathering can compensate. The positive feedback will engage, and Earth will follow its twin across the same invisible line. A reasonable objection. 1 billion years is not urgent. That's true for the natural process, but the physics that killed Venus isn't unique to Venus. Carbon dioxide trapping infrared radiation, water vapor amplifying the warming, positive feedback eroding stability. These mechanisms operate identically on Earth. The same equations, the same molecules, the same thermodynamics. What differs between the two worlds is not the process, it's the pace. Those Venera 13 photographs are still the highest resolution color images ever taken on Venus. Flat basaltic rock stretching to a blurred horizon under 90 atmospheres of carbon dioxide and 460 degrees of trapped heat. An amber glow. Sunlight filtered through 100 kilometers of atmosphere until it barely resembles sunlight at all. Those rocks may once have sat beneath an ocean, on a world with weather, with shores, with time enough for something remarkable to begin. The most dangerous place in the solar system isn't dangerous because it's alien. It's dangerous because it's familiar. Earth's twin didn't become hell through some exotic process unique to its corner of space. It happened through the same greenhouse physics that warms your morning, the same molecular interactions, the same feedback loops, pushed past a threshold where the system could no longer pull itself back. Every feature of Venus's destruction, the crushing atmosphere, the surface hot enough to soften metal, the chemical signature of oceans torn apart molecule by molecule, is the logical endpoint of a process that begins with sunlight warming a planet with carbon dioxide in its air. Could the same thing happen to Earth? The physics doesn't distinguish between planets. The same equations govern both worlds. The only difference was 30% of an orbital radius, one step closer to the Sun, and this is what became of a world with oceans. Venus is not just the most dangerous surface in the solar system, it is a message, inscribed in the deuterium ratio of a dead atmosphere, in 460 degrees of trapped sunlight. in the silence of a probe that lasted 2 hours and 7 minutes before the planet took it back. A message that says, "This is what happens when a world like yours crosses the line." And we, with the thermostat still running and the oceans still in place, are the only ones who can read it.
For a limited time only, we are giving out the first 3 chapters of our complete introduction to stargazing completely free. Check our page info for the link.